Welcome, ladies and gentlemen, to Warwick Sciences Film Practical, which is on levers. Now, a lever is simply a rigid bar, and in this case we've got a ruler here that balances around a fulcrum or a pivot point. Okay, and we've got a pivot point here in the shape of a triangle. Okay, now what we're going to do is we're going to try and see what the effect of a lever is. Now up the back here I've got all the different types of levers. We have first class levers, second class levers and third class levers, and I'll go through and run through those after the practical. As always, there's a prac write up, ladies and gentlemen. If you could write that up please, and then when you're ready you can start the practical part of the video. Okay, now our load is going to be 20 or 250 grams, and we're going to place it at 15 centimeters away from the fulcrum. So it's on 40 there, it goes back to 25, so it placed at 15. So that's 250 grams. Now what I'm going to do is I'm going to add load onto this side here, okay, or add effort, sorry, not load, but add effort onto this side in order to see if we can get it to raise up. And then at the point where it actually does raise up, then we'll have a look at all the various numbers. So let's take it 5, and this is 100 grams, and we put it at 5 centimeters away from the fulcrum, and we don't have anything. We put it 10 centimeters away from the fulcrum, and we still have no movement. Now we put it 15 centimeters away from the fulcrum, we've got no movement. We put it 20 centimeters away from the fulcrum, we have no movement. And we put it at 25 and we've still got no movement. So our effort arm is going to be greater than 25 centimeters, but our load arm, which is always going to be the same, is basically 15. So let's add on another 100 grams and go for 200 grams. So let's place it 5 centimeters away and we have no movement. Let's place it 10 centimeters away. We have no movement. Let's place it 15 centimeters away. We have no movement. Let's place it 20, and it just started to lift off at 20 centimeters, ladies and gentlemen. So with 200 grams, the effort arm is going to be 20 centimeters. Let's now look at 300 grams. So we'll add on 300 grams. So we go to 5, we have nothing. We go to 10, we have nothing. 15 centimeters away, we have movement. So that's 15 centimeters away with 300 grams. And let's do the same now where we get into 400 grams. Okay, now what I might do with that, 1, 2, 3 is use one of these, which is a little bit safer. So let's put it 5 centimeters away. This is 400 grams. The effort arm is obviously this side, the load arm is this side, it's still 15 centimeters. Then let's put it at 10 centimeters and we start to get movement. Okay, so what that will show is that if you increase the effort, which is in this case the masses, then it is actually closer to your effort arm, which is the distance between your fulcrum and your effort, actually becomes a bit less. Now what we want to do with levers, of course, though, is we want them to do what's called a mechanical advantage and make life easier for us. We don't want anything to make us harder, so we actually want to do it a lot easier. So let's have a look at this setup here. Okay, now I'll just move these ones around because they are actually pretty big and heavy. So what I've done here is I've simply made 3 first class levers, and the first class lever always has the fulcrum in the middle, but what I've done is I've put the fulcrum at different positions. So in this case the effort arm and the load arm are the same. In this one there's a greater load arm than effort arm, and obviously there's not much of an effort arm here. Now what I'm going to do is add the same weight to each and then screw it down. So what I've got there is 2 kilograms. Okay, and screw that one down as well, and then screw this one down as well. So the question is, what effect does the effort arm have in terms of having to lift those? So here we have the effort arm and the load arm the same, and that one's pretty easy to be able to do there. I've made the effort arm shorter, I've increased the load arm, and as you can see, it's actually a little bit harder to do. And now I've basically got no effort arm at all, very much load arm, and really hard to lift up. So what this shows us is that if you can have a short effort arm, a short load arm and a longer effort arm, that'll make life easier and you'll get what we call a mechanical advantage. So this is why if we're trying to get the lid off something, we use a very long screwdriver in order to rake it up. Crowbars work on this approach too, so you have a really long crowbar if you want to move a rock or move something, because you have a very long effort arm compared to a very short load arm. Now the second type, or the second class of lever, is the second class lever, of course. Okay. Now again, these ones have the fulcrum at one end, the effort at one end, and the load in the middle. So again, we're talking about load arms versus effort arms. Let's place this one in there. And again, these are all slightly different positions of the effort, and it's going to be about which one is going to be easier to lift up. You might want to have a bit of a guess, although we don't guess in science, we have predictions, don't we? So let's screw those down. Alrighty, now I'll just turn them this way because it just makes it a little bit easier for me to do. So this one here, our first one has a very short a very short load arm and a very long effort arm. This one is about equal, and this one has a very long effort arm and a very short load arm. Okay, so you might want to sort of guess which one is going to work the best. This one, yeah, I can lift that one up. It's got a bit of weight attached to it though. Okay, that one becomes a lot easier, and this one really easy. Okay, and this is the concept behind the wheelbarrow. Okay, with a wheelbarrow we have the wheel, which is the fulcrum, we have where you put your load, and then you have your handles. Okay, so that one's, look at that, easy as compared to this one, which is a lot harder to do. So again, the shorter the effort arm, the harder it is in order to lift up the weight. Okay, so now we get into our final one, which, not surprisingly, and as I always say, scientists are really clever but not very creative, we call it a third class lever. And the third class lever has a fulcrum at the end, has the effort in the middle, and it has the load at the end. So this is an example of a fishing rod. Okay, this would be tucked into your belly here. Okay, you would be grabbing the rod there, and then hopefully the fish is attached to the other end. Okay, so let's, now again, the different positions of the effort arm here, load arm there. Okay, because it's the distance between the effort, which is the knob, and the load that's there. Okay, so this one is pretty much right on by the time we do that. This one's close to the middle, not exactly in the middle, but it's pretty close. And this one is right there. So again, you might want to have a bit of a prediction as to which one is going to be the easiest. So I'm going to start off with the one that has the very long effort arm and very short load arm. And that one's actually not too bad to lift up. Okay. Now, as we move the size of the load arm, okay, becomes a little bit harder because our effort arm is short. And if I do it there, it's actually really difficult in order to get that up. Whoa, getting a bit too old. So again, the size of your effort arm becomes important, and when you work out exactly what a mechanical advantage is, and when we talk about a mechanical advantage, is that's how much easier it is. The mechanical advantage is the size of the effort arm divided by the size of the load arm. So as you can see here, it would be this size here, which is the effort arm. This size here, the effort arm, and you would divide that by that side there to make it easier. And just to do a measurement, we've got about 23 there, up against about 9 there. So it would be 23 divided by 9, which comes out to around about just 2.3, 2.2, 2.3. So having it there makes it 2.3 times easier. If we go to this one, 9 divided by 27, okay, that makes it, well, actually that makes it a lot harder. So if you went 9 divided by 27, which is 0.3, that's basically a lot harder. So that's basically how we work with levers, ladies and gentlemen. Okay, a lever, fixed bar around a pivot point, which we call the fulcrum, and it's the size of your effort arm. If you can make that as long as possible, then you will have an easier amount of work to do. As always, ladies and gentlemen, please fill in the worksheet and then consult your teacher if you have any concerns on levers. And thank you for accessing Warwick Science's Film Practical on levers.